Welcome everyone to another Power Lunch presentation. Today we have Marilyn Cresswell, who is a librarian-in-residence at the Copyright Office, and Kelly Bills, who is a librarian-in-residence in the Geography and Maps Division. I'm going to turn it over to them so they can present their panel, which is probably the most fascinating topic that I've heard of in a while, and I hope you enjoy it too. Kelly?
Thank you, Donna. Hi, I'm Marilyn Cresswell, and I would like to welcome you to Mapping the Final Frontier, a conversation about the universe, GIS, and copyright, which is part of the Librarians-in-Residence Power Lunch series. Thank you all for joining us today for this exciting panel discussion about the Library of Congress's astronomy map collection, modern uses of celestial maps, and the issues we face when it comes to using these maps. I would like to introduce my co-moderator, Kelly Bills, who will be our technical moderator, making sure the technology works for us and watching for your questions in the chat box. Each of our panelists will have about 5 minutes to share the ways their field of expertise intersects with celestial maps, and I will be asking some questions before we spend the last segment answering your questions. On this WebEx platform, we ask that you put your questions in the chat box to Kelly instead of in the Q&A section. Please know that this session is being recorded. Without further delay, I would like to introduce our panelists. First, we will hear from J.J. Harbster, who is the head of the Science Reference section in the Science, Technology, and Business Division. Next, we will hear from Josh Levy, a specialist in the history of science and technology within the Manuscripts Division. After Josh, we will hear from John Hessler, who is a specialist in computational geography and geographic information science. Once we hear from these experts on the maps themselves, we will have the pleasure of hearing from Whitney Lewandowski, Attorney Advisor to the Office of Public Information and Education within the U.S. Copyright Office. I'm excited to learn and engage with these panelists, so let's get right to it. JJ, please take it away.
Welcome, everyone, and good afternoon. Happy Friday. Thank you for joining us today, and I just want to also thank Marilyn and Kelly for putting this panel together. So part of my job and the job of the library science librarians that I work with is to help develop and assist with the discovery of the science and technology collections. Now, most of the material we work with are published monographs and serials, which do contain maps, charts, and illustrations. And astronomy is a subject that is very near and dear to my heart, and I've spent a lot of time learning about and discovering the astronomy collections. And let me tell you, they are some of the best in the world at the library. Next slide. So whenever I give a presentation about the library science collections, I always start with Thomas Jefferson. He had a strong interest and knew the importance of science would bring to our developing country. And he helped to form the early purchases at the library, which expanded the narrow focus to include science. And in 1815, Jefferson sold his personal library to Congress, which I would argue established the foundation of the library's science collections, in which we continue to build on today. There is a lot one can say about Thomas Jefferson, but did you know that he was also an astronomer? The study of astronomy and its practical applications intrigued him, and this is evident in his letters, his personal letters, and his library collections. He stressed the importance that astronomical observations be established in the United States and that ephemeris be published also here in the U.S. And he also made his own astronomical observations and calculations. And the most notable is the solar eclipse in September 17th, 1811. And he wrote about Herschel's discovery of Uranus, which happened around that time, and work about the discovery of double stars and variables. Now, another significant milestone in developing the library's collections came via the Smithsonian deposit. By 1867, the collection amounted to around 40,000 volumes, and when all was said and done, we estimated that around 500,000 items were added via the Smithsonian deposit. This collection is especially abundant in scientific memoirs, transactions, periodicals of learned scientific societies, museums, exploring expeditions, and observatories throughout the world. And arguably, one of the most important contributing factors in developing the library's collections was the Copyright Act of 1870. Librarian of Congress Spofford reinstated that material registered for copyright in the U.S. required to deposit a copy at the library. And this helped grow and continues to help grow the collections immensely in all areas of study and formats, especially materials related to the sciences. Next slide. So the library also obtains material by purchase, by exchanges, gifts, and transfers from other government agencies. The library has exchange arrangements with institutions throughout the world. And I cannot talk about the library's astronomy collections without acknowledging the work of legendary astronomy bibliographer Ruth Freitag, whose work inspires me daily. She immersed herself in the library's astronomy collections and delighted in compiling epic, and I mean epic, bibliographic guides. She compiled comprehensive bibliographies on the Star of Bethlehem, Halley's Comet, and women in astronomy. And when Carl Sagan was writing his book about comets, Ruth was there to help. In his introduction, he noted that the best part of writing his book was meeting Ruth. Next slide. So now I turn to the theme of our panel, celestial maps. So in order to map the cosmos, you need astronomical observations and data. And we collect this material in all forms and periods throughout history. Our collections represent a history of looking up at the stars and beyond, from classical astronomy that focused on positional astronomy and celestial mechanics to this new astronomy or modern astrophysics that began around the 1860s when the quality and quantity of starlight radiation was studied by the use of photometry, astrophotography, and spectroscopy. So our collections represent observations and data from the earliest times to today that use the naked eye or pre-telescope, terrestrial telescopes, and now space-based telescopes to observe our universe. Next slide. One of my favorite collections is the serial sets of observatories from around the world. These places are part of our cultural and scientific heritage. This collection contains data and research findings from a variety of ground telescopes that sought to determine stellar coordinates. Now, with this collection, we can see the shift of astronomical observations moving away from the classical astronomy to the new astronomy of spectroscopy and astronomical photography to map and understand the universe. Next slide. Another wonderful collection are the expedition and observation reports related to astronomical phenomena, such as eclipses, comets, and transits. These reports are chock full of charts, tables, graphs, images, maps, and also personal accounts. Next slide. We also have atlas, celestial atlases. The atlas is a published medium that takes all of the data and observations to illustrate the sky, often in its entirety. They're important to scientific study, but they can also be artistic works of beauty. We have historical and new atlases in our collection. And these celestial atlases are not just for the scientific community. They can also be of interest to the public who want to learn more about our universe. Next slide. And lastly, I want to plug our NASA lecture series. This public program invites Earth and space scientists from Goddard to the library to share their research and findings. Most importantly, they illustrate the tools, such as space-based telescopes, that aid in their observations and data collecting. And you can view those past lectures from our website. Next slide. Thank you. And those are just references.
Okay, I would like to build on JJ's presentation by highlighting some of the primary sources related to celestial maps and especially resources in the manuscript division. And in the process, I will tell a quick 5-minute story about the history of American astronomy's relationship with maps, America's relationship with astronomy, and how our maps of the sky were demystified. Next slide. There we go. So while I have this partial list of the manuscript division's astronomy collections up, I'll just point out that the history of celestial maps, of course, is much more extensive than I'll be able to address today. We know, for example, that in the 3rd and 4th century BCE, Chinese astronomers were mapping the positions of the stars. We also know that the Greeks produced a star catalog around 129 BCE, which built on sources going back to the Babylonians. And we also know that the aim of those maps wasn't just to represent outer space, but to represent our inner space as human beings. In other words, pre-modern and early modern celestial maps were in many ways mystical documents that reflected both astronomical and astrological knowledge. Next slide. So as JJ pointed out, Thomas Jefferson, like other early American elites, owned a telescope. He made his own observations, and he pursued a rich astronomical correspondence, which you can see in the library's Jefferson papers. Astronomy was a popular pursuit in 18th century America, but with no institutional observatories until the 1830s, skilled astronomers like Andrew Ellicott were forced to seek other kinds of work. So Ellicott used astronomy to create terrestrial maps, including the first survey map of Washington, D.C. His surveys revolved around his observatory tent, where a skilled assistant would lay on their back all night with a sophisticated zenith sector, sighting through the eyepiece to observe stars as they crossed the meridian, and then producing figures that Ellicott could refine to determine latitude. Next slide. Ellicott's assistant in Washington, the self-taught free black farmer Benjamin Banneker, had already been spending all of his free time making observations and experimenting with calculations of celestial positions before he and Ellicott ever met. So when the survey was complete, Banneker leveraged his enthusiasm and his reputation to produce his version of a document that really stood at the center of astronomy's popularity in early America, the Almanac. Banneker's 1793 Almanac, which you can see here, doesn't contain any maps, but it does contain data on the positions of the planets and the stars, which you see in the middle, and items like astrological charts, which you see on the left, as well as essays on politics and religion, currency conversion tables, and courthouse calendars. In other words, it was a popular document, a document that both reflected American enthusiasm for astronomy and helped to generate it. Next slide. But in the 19th century, positional astronomy was becoming obsessed with mapping. And as astronomy was becoming a badge of national achievement and institutions and governments were competing to build observatories as symbols of order and progress, observatory work itself was becoming much more specialized. Increasingly, assistants spent long hours recording fixed star positions and then carefully reduced that data for publication. The U.S. Naval Observatory, which was established in 1842, hired human computers to do those calculations. Among them was Maria Mitchell, who was a Nantucket librarian by day and a diligent observer of the positions of Venus by night. Mitchell recorded pages of observations in tiny, tiny handwriting for publication within the Naval Observatory's own almanac, which recorded astronomy in the language of mathematics in hundreds of pages of raw data, just as other observatories did, without any history or poetry or astrological insight. Next slide. Simon Newcomb later reminisced about his early life in the Naval Observatory before he became its director, when there was a, quote, free and easy way of carrying on work, and when instruments failed often enough that the astronomers could vote it cloudy when they got tired and disappear to a restaurant for a plate of oysters. But he also recognized that the increasingly tedious nature of the work that was helping divide professional astronomers from popularizers who still explained astronomy in the language of poetry, astrology, ancient myths, and divine explanations, it was instrumental in producing the modern observatory. And in many ways, the modern observatory was becoming the model scientific research institution. Next slide. Of course, the observatory's human computers were replaced with machines, and new instruments like spectroscopes enabled a radically different kind of celestial mapping that was carried out by professionals like Vera Rubin. And even as professional astronomy grew more sophisticated, now expressing itself increasingly in the language of physics, the maps and the images that it produced grew increasingly representational, vivid, and even beautiful. Next slide. So when the Viking landers touched down on Mars in 1976 to image and study the planet, astronomers like Carl Sagan saw the beauty and anticipated an enormous public interest. But to his surprise, that interest didn't materialize. So he created the miniseries Cosmos as an attempt to bridge professional and popular astronomy and reintroduce the public to the magic of astronomical observation. Next slide. Okay, so before we finish, let me just take a cue from Cosmos and go a little bit more global, just to highlight a few of the other items at the library that offer alternative histories of celestial mapping. The first one is a book that's held in the Asian division. It's Baba Nobutake's Elementary Astronomy. This is part of a collection that includes things like a book of 18th century South Asian hymns for getting rid of planetary influences, and a 19th century Buddhist cosmological map from Japan that is gorgeous. Nobutake was a physician in Kyoto. He was a polymath and he was a popularizer of Chinese knowledge and culture, and himself an influential practitioner of divination. And his book integrates Chinese astronomical knowledge with astrology and with Copernican astronomy, and it helps to reveal Japan's own complicated position in the world at that time. Next slide. The other item that I want to highlight is a stick map from the Marshall Islands, which is actually one of 3 held by the Geography and Map Division. This stick map is not a map at all. It's a memory device with shells that represent islands whose positions don't correspond with their physical locations. Instead, the map trains the eye of the traditional navigator to measure the way that islands disrupt the pattern of deep ocean swells against the rising and setting points of specific stars and constellations, and then to use that information to steer an outrigger canoe across the open ocean. So just to wrap up, these celestial maps, they have human histories, and as primary sources, they can reveal as much about the people who made them as they do about the rest of the universe.
Well, thanks, Josh. That was great, and thanks, Jennifer. I'm going to build on that a little bit by moving more into the modern era. One of the most important things that's been happening both in computational geography and cartography and in astronomy is data. I would really argue that we are in the super data age of astronomy, and that has presented all sorts of problems for traditional libraries. The last significant map in paper form that the library obtained that's in the Geography and Map Division is actually a complete collection of all the sheets of the Palomar Deep Space Survey. It's on thousands and thousands of sheets held in our vaults, printed in on exquisite paper and in exquisite detail. In my 25 years almost at the library, I have never seen a single person actually pull that particular piece, simply because we have increasingly become data-driven and things have become more interactive. So the next slide. So today, astronomy has, as I said, changed a great deal. That Palomar data and increased data from that Palomar survey are now found on the Sloan Deep Sky Survey website. Not only can you get images of any of those bodies and thousands and millions more, but it also has interactive spectra of each of these objects. One of the problems with library collections at this point is that this particular website, for instance, the functionality of it cannot be archived. Also, the data in it is much too deep, much too big to actually be archived by a traditional library. This particular group also has what is a machine learning program operating on it. So when I bring up a field of the sky, I can ask the computer to identify all of the objects, and it will actually draw little bounding boxes against all the objects and then map those objects and allow me to interact with those objects in very profound ways. Now, this particular database can be accessed at the library and other libraries around the world, but it's becoming increasingly more difficult for traditional science libraries to keep up in any of this kind of data collection. Next slide, please. So when we look at some of the major projects that have been going on recently, everyone probably heard about the first image of a black hole, which is the image on the left-hand side there. Basically, the images and the data for this was 350 terabytes per day were taken in data, and it took 4.5 terabytes of data to actually build this one single image. Now, obviously, the Library of Congress and no other library can hold that amount of data. And so this has become an increasing problem. The new Deep Galaxy Survey at Caltech is pulling 200 terabytes of data per day, basically mapping all of the galaxies in the universe in 3 dimensions. There's about to be a group of radio telescopes that will come online in late 2023 that will pull more data out of the sky per hour than all of the information held in all of the books in the Library of Congress as we speak. That amount of data is just impossible for libraries to keep up with. Next slide. So in a real sense, traditional library collections are becoming very much insignificant in the actual research edges of astronomy and mapping, simply because of this serious data problem. The Stanford protocols and the MIT protocols on astronomical data and publication are also presenting big problems. Those protocols basically say that a published paper in a journal on a computational aspect of astronomy is an advertisement for the scholarship as opposed to the scholarship itself, and that the scholarship must be produced and contain all of the data and the software environment in which that information has been found, which again pushes this out of the traditional library environment and more into the institutional environment. Something like the Deep Sky survey that replaced Palomar, as we see here. On the right-hand side, you see the actual images, but on the left-hand side, you actually see the way the data is stored. Every one of those strips is one of the objects in these particular image. So the data is not even stored in a way that's visualizable without the computational software. So when I actually go to this website, when I actually go and I look at this data and I want to look at an object, what happens is the software pulls the line of data, next slide please, and then reconstructs this. So this particular image that was in that right-hand image doesn't exist until I ask the computer to reconstruct it for me. So there's nothing to actually collect except for those long strips of data that would then have to be computationally reconstructed. Again, this is a difficulty for traditional science libraries, and this runs across all the sciences which are relying heavily on computation. Next slide. Perhaps the newest problem, the newest difficulty is really the way data is being stored and then being accessed. Basically, increasingly in large data projects, both in physics, in astronomy, and in some of the areas where I've been recently working, for instance, in the bioinformatic mapping of the SARS and COVID data, the genomic data that is coming out. Increasingly, machine learning and artificial neural networks are becoming key to the actual way that we look at this data. So one of the big projects that's actually taking place right now, and you probably, years and years ago, there was a crowdsourced project where you would go in and identify different galaxies, the shapes of galaxies, and that would be a crowdsourced project. But now generative neural networks and convolutional neural networks have surpassed human abilities to actually do that. So the next slide, please. So basically what we have is we have these very big projects where we have tons and tons of data being moved from various telescope sources. So in this case, the project I'm talking about here is a galaxy classification project where we have something like 70 petabytes of data, a huge amount of data, which basically a generative adversarial neural network, which is a type of artificial neural network, has basically implementing a generative model and is basically working its way through all of those images. And what I would do for this adversarial neural network is I would query it. So this data would be sitting in a data storage area, and I would say, listen, I'm looking for all of the particular galaxies that have this shape, this magnitude, this piece of the spectrum. That data, that adversarial neural network would then go in and then look at all of the images of these things and pull all the data I needed. So in other words, it's the combination of the massive data plus the artificial intelligence things that are working behind it that are actually generating the data at the moment, as opposed to the data being there to be stored. And so, as I said, this has created quite a difficult problem for libraries like the Library of Congress, as most of this sort of thing is being done online in formats that aren't being archived simply because of the impossibility of that. And so really where we are right now is we're at a crossroads. And there's nothing wrong with any of this. I mean, information has often changed through history, the way it's been stored, the way it's been accessed, the way it's been sent through. There's no a priori reason that a library like the Library of Congress it should be storing this sort of data or can store this data. It's just a change in the way things go. And so increasingly, places like the Library of Congress are becoming less on the research edge and more in the historical sampling of what is going on in these fields. But it is a serious problem, and it's a serious problem both in traditional cartography, that we're struggling with geospatial data, and with astronomy. So thanks everybody for listening.
Hi, good afternoon. Trying to clean up on this one is a pretty heavy task, and so I'm going to give it a shot. So we heard from JJ and Josh, who were talking about the different varieties and the legacy of astronomy maps within the library's collection. And in both of those presentations, what we saw was a lot of the wide variety and expressive choices that go into the creation of celestial maps. And then John just gave us a super deep dive into contemporary data issues. And I'd like to tease out those data and expressive threads from the previous presentations to focus on some of the copyright concepts that we are bringing to bear when we talk about celestial maps. So next slide. Maps are a central part of copyright law. They are part of they were part of the original Copyright Act of 1790. That was the first federal law passed by a new Congress. And I would be remiss if I didn't mention that copyright sources back to the Constitution, Article 1, Section 8. So when we are talking about maps being protected by copyright, we are talking about a legacy that is constitutional in basis, and also then hundreds of years of sort of continuous copyright protection. Now, the law has changed since that first 1790 federal copyright law, where the requirements for copyright protection were to register the work, the published work, for a book, a map, or a chart with the District Court of Philadelphia. And I will admit, when Josh mentioned Benjamin Banneker's encyclopedia, I tried to take a quick peek at the library's records of early copyright registrations, and I would definitely suggest checking it out to see if Banneker's encyclopedia is there. I wasn't quick enough to do it, but we should find out. Next slide. So really, I would like to just touch on 4 copyright principles that helped us to understand the relationship between copyrights and maps. So today, copyright protects a work of original expression from the moment it's fixed in a tangible medium. So this looks a lot different than from what we saw in the 1790s. But we're looking for the original expression of a map. And when we say that it's an original expression, we're thinking that it's independently creative and it's independently creative and minimally creative. And we're looking for creativity that is owed back to an individual author or authors. And with this, we know that copyright only protects the expression of a work, never an idea, a fact, discovery, or concept. And this sort of helps us to then tie what we've seen before in the presentations, where we've had some examples of some very expressive works and maps. And then we've also taken a look at the hard data that goes into maps. So we can see that there is a relationship in maps between the expression that's protected by copyright and the data, the facts, the discoveries that will not be protected. And one of the things that we encounter when we have this relationship between creative expression and data is that when we get very close to being able to express that data in a limited amount of ways, that we say that, well, the data is going to rule. And we're going to say that there's no copyright protection when there's a limited way of expressing the facts, the discoveries, or the data that underlies a work that might be protected by copyright. So what I wanted today is to focus on a particular type of celestial mapping that can resonate for us as expressive works. Next slide. This is an example of types of maps that will not be creative because the facts of the maps that are contained in the maps are so close to the expression of it that we need to recognize that there's going to be public protection or public availability for those maps. So if you can imagine if we were to provide a copyright monopoly to a map of the United States that we see on the left, or the Great Lakes that we see on the right, or the outline of Michigan, that we would very quickly run into a limited expansion or limited sharing of knowledge. And we really want, through copyright law, to provide a promotion of progress of science and the useful arts. So we have things that are basic understandings, facts, data, the foundations of our understanding of life are going to be available to the public. So these things here that I have on the screen, not going to be protected by copyright. Very simple. Next slide. But the works that I'm going to be focusing on in the second half of my presentation today speak to us in a very different way from an expressive standpoint. And so from now on, I'm going to be talking about images from the Hubble Space Telescope. The Hubble Space Telescope is a telescope that helps the scientific community to map space both near and far, particularly focusing on ultra deep space, and we'll talk about that in a second. And then this is a collaboration between NASA, so the U.S. Space Agency, the European Space Agency, and then the Space Telescope Science Institute. And the wealth of images that they have produced all relate back to maps and to copyrightable expression. And expression is important for mapping the products and the data that's gathered from the Hubble Space Telescope. Next slide. I might offer to you that every image that you see of space is a map in and of itself. And the reason is that when we see a space image, what we are seeing is the transmission of different wavelengths of light. And when we are talking about space, we are talking about light as both a luminescence, a quality of physical being, but also a measurement of space and time. So when I would offer that when we are seeing space images, that every time we see a space image, we are also seeing a map. We are also seeing information about space and time and location. And you can see this in an example here from the Hubble Space Telescope, where they've released two images. On the right, what we have is we have a compass and a distance measurement, a scale. So something to keep in mind as we look at, when you look at images of space, what you're also looking at is a map. You're telling celestial geography. So next slide. And when we get these images, when we get all this data pulled from instruments that like the Hubble Space Telescope, what we're seeing, oftentimes the data that we receive is going to be non-visual data. And so what we can see is only a small section of the actual wave of light that space emits. So what I have here on the right is an image of the Hubble ultra deep field image. That's in this image, every point of light that you see is actually a representation of ultraviolet light. And so when we receive that ultraviolet light, there has to be some sort of translation and some sort of analog from that ultraviolet non-visual light into visual light so that we can understand what we are seeing in space. And so that is where we start to see human authorship and creative expression come in, because these choices are often made by scientists, by visual artists who work in conjunction with scientists, and by photographers and graphic designers. And so this team works together to help translate these images so that they are legible and understandable to a variety of audiences. Now, a small, little asterisk hitch that I won't touch on today, but what John sort of mentioned about machine generation of images from data, that puts us into a different question with copyright creation because we know that expression has to be owed to a human author. So I'm just going to put that into everybody's brain so that we can talk about that some other time. But it's an interesting question that sort of transcends our topic today of what it can be owed to a human and what can be owed to a machine. So here what we have is we need the human expression in order to understand the scientific data that we receive from the Hubble Space Telescope. Next slide. There's also a question of audience. So there are many types of people that are going to view a celestial map. There are scientists. JJ mentioned in her presentation with the celestial atlases that they are both scientific objects and aesthetic objects. So celestial maps can have an interest to scientific communities, to hobbyist communities, and to a general public. And the important role of expression in this scenario is how does expression help different audiences understand the maps that are put together based off of data from space. And so here I have 3 images of the Crab Nebula, and each image represents different wavelengths, so different measurements of space and time. So on the left, I have an infrared, on the middle, I have an X-ray, and on the right, I have an optical. And so we know that already choices are being made in order to translate X-ray and infrared light into some sort of visible, readable spectrum. But also, these types of images are perhaps understandable or of interest to hobbyists, to people with a background in science. But for, so a layperson, say like myself, seeing these 3 images might not give you a great sense of what the Crab Nebula is. Next slide. And so this is another part where creative expression becomes an important role in celestial mapping. So here I've provided a composite image that has been released for general public consumption from NASA, from the Space Telescope Science Institute. And here what we have is a composite of those 3 original images that have been combined and manipulated in order to give a better sense of what the Crab Nebula is. So for me, for an average person who might not understand the underlying astronomical principles of different types of light and distance, but I can take a look at this composite image and understand something about space and the relationship between the different elements in the Crab Nebula. So here we have another example of how expression is essential to mapping the sky. Final slide. And so there was a question of where do we get maps and how do we access maps? And JJ and Josh had provided some great examples of how we can access maps through the library's collections. And John had detailed some of the challenges of representing or accessing data related to maps when we have such a large chunk of data these days. But know that for a sort of a non-expert audience, we have different ways that we can access maps. So for example, all of the Hubble Space Telescope images are in the public domain. And when you have maps that are produced by federal employees in the course of their employment, those works are going to be free and available for everyone to use. Also, maps that from 1924 and before are going to be in the public domain. And sort of, again, any of that data or maps that contain the data, the underlying data will be accessible and usable from everyone. Because again, remember, we want that underlying knowledge to be available to everyone. And then also for maps that are proprietary or are still protected by copyright, there is also a robust system of licensing. So there's the direct to copyright owner licensing system, but then there's open access licenses, which allow people to use and reproduce and share those maps, usually under some conditions such as crediting. And that's always important to check the terms whenever you enter your license. So this is just a really quick trot through the intersection of celestial mapping and copyright, where the real things that I want you to take away from is that expression is extremely important to mapping things that we cannot see. And then also, though, that we've got some tension that's underlying between the creative expression, whether it's created by a human or a machine, and then the expression and the data. So thank you.
Thank you, Whitney. I want to remind all of our attendees that you can enter your own questions in the chat box. You can direct them to Kelly, and we will make sure that they get answered. So to start us off, I've got plenty of questions of my own. So I'd like to know more about the intersections between these types of maps. I know that there are ongoing efforts to apply terrestrial GIS information to historical maps, like the Library of Congress's Sanborn map collection. Do you know of any similar hybrids of historic and GIS mapping for astronomy data, or what are some other ways you can imagine these two types of collections informing each other?
That's a difficult question. Really, when we think about astronomical phenomenon, it's happening on such long time scales that the idea of a historical map that would have been made in any historical time where man is alive, the real differences between what's happening on the spatial scales that we're talking about are very limited. We could talk about things like looking at mapping magnetic fields, the changes in magnetic fields and things like that, which we do have interest in very recent historical data. The Earth's magnetic field, the sun's magnetic field, where those things are changing on scales that are more relevant to where we are today. In the traditional mapping sector, obviously, this has become really important and really critical because with things like climate change, with things like melting ice caps, historical maps have become more relevant than ever because one can geo-rectify those maps, put them on top of modern maps, and really begin to quantify the changes that you see on terrestrial timescales. But on the celestial timescales, things are happening at such a distance and over such longer periods of time that the human distance between modern mapping and historical mapping has very little relevance. There is a lot of GIS being applied, though, and this sort of thing by amateur astronomers. Asteroid hunters, things like that are using very simple mapping tools that are either available online or available through GIS and software providers to really inform their work, which is, important. There are many amateurs now who still are making discoveries in things like asteroids and extra solar system bodies that are just not of interest to the big programs. But as far as that goes, it's the time scales are just too long.
Josh or JJ, how are you seeing the historical maps being used today, either with GIS technology or not?
I kind of have to think about that one, but I do have a recent thing, but it's not celestial maps. They're maps from the hydraulic office, so like coastal maps done in the 1800s. So we recently been working with a USGS scientist who's been looking at a lot of these reports from the late 1800s. Sort of mapping winds and currents and tracks through the North Pacific. And he has been really happy to know that we have some of these maps from the 1870s that he tells me is going to be a big discovery if it shows what he thinks it shows. So I do have a recent thing for that. I mean, I think it all depends on the questions you're asking. So what you're asking is going to depend upon, what sort of resources you're going into. And, I could say when Ruth made her Star of Bethlehem bibliographic guide, she went through all sorts of observations of what people thought was the Star of Bethlehem. Was it a comet? Was it, a planet? Was it whatever? And so those were questions that people still actually, I don't think there's any conclusion on what exactly was the Star of Bethlehem, what exactly it was. But, so it's those type of questions you're asking. And so I think that's what it depends upon.
And maybe I'll just hop on a little bit to suggest that I'm actually not aware of any historians that are working on projects that use GIS to assess celestial maps, although there may be such projects. But I do, like Jennifer, know of similar projects that use GIS to examine historical terrestrial maps and use it very creatively. I know of a project that, a brilliant project that's kind of an environmental history of the early settlement of Indiana, where GIS mapping is being used as a way to contest the idea of a kind of blank landscape that settlers built out from nothing, and in fact uses this mapping data to find all of the different ways in which indigenous people had cultivated land and then prepared it for later use. And all of the land that was richest under indigenous cultivation then became the richest land that was used under settlement, and that really shaped the settlement of the entire state and other states as well. But as far as celestial maps, I'm not aware of anything myself.
That is really interesting. Today's astronomers have the benefit of this amazing technology, so much data from such faraway places, and to take photographs and collect samples. How might this reliance on technology change how we make astronomy maps today, whether handmade or computer-aided? And tapping on Whitney, how does that computer authorship play into copyright?
I would do this one.
So I will start by saying that I do not have specific insight into the larger mapping industry, so I would, or larger mapping practices by scientists, so I will leave that to the professionals on the panel. I think what I would highlight is some of the larger tensions that we have across industries about the relationship between human authorship and computer-aided development, specifically in the AI sphere. And really, what we're looking for is where's the human hand? And we've had these sort of encounters with copyright throughout history. So when photographs were first came about, there was the question of whether or not that there was a human author involved in the production of a photograph. And then when we had computer-aided development, whether or not that there was a human hand when we have computer-generated images. And each time that we have been able to resolve and been able to analyze and figure out where the human hand is, and we recognize that human authorship. So I imagine that if you were someone who is engaged specifically in the mapping sphere, as a copyright person, I would say to the map expert, asking, well, where's that human hand in your work? And that is where we can start the question of creative expression.
Hey, Kelly, how are the audience questions coming? Are they rolling in?
Mm-hmm. Yeah, we have 2 questions if we want to address them now.
Yeah.
All right.
Let's get to those.
All right, so the first question was from the National Library Service asking about accessible maps and if there are any efforts going on at the library currently about making these celestial maps accessible from the collection.
Well, that's a good question. There's a digital digitization program going on at the library. It's not concentrating on celestial maps, but there are a great many celestial maps that are, in fact, up online. I can think in terms of things like some of our Ptolemaic atlases, some of our Renaissance materials. Certainly things like if you look in the rare book division, you'll find a beautiful copy of Galileo Sidereus Nuncius with some beautiful stellar maps drawn in there. And so the library does have a fairly active digitization program, which has been making these things available, at least digitally. There are certain other accessibility concerns, some of the disability accessibility concerns with celestial maps, and mapping in general has had a very difficult time with the disability community. In fact, in trying to figure out how to make maps, especially digital maps and GIS, actually available to that community, and it's an ongoing project. Some of the things that the library has been doing with their story map program, which has been headed up by Paulette Hazer and by Tim Saint-Onge in the Geography and Map Division, have come up with ways to actually make story map data and the map data actually available to the people who are visually impaired, and have been working very closely with accessibility people. So we have both of these things kind of going on, which are going hand in hand. But there is no actual program to make all the celestial maps that we have available. There are many, 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 but online in the digital collections, there really are plenty.
And John, don't we have tactile maps and geography and maps that you can feel and touch?
We do. We have tactile maps that you can feel and touch. There are actually some celestial ones also. There's even certain maps that weren't necessarily meant to be tactile that can actually be tactile just by the way that they have been designed. But there still needs to be some sort of metadata expression to kind of key in exactly how they work. But yeah, we do have a collection of those things also.
All right, thank you. And then the next question is about machine learning enabled images that John, you showed in your presentation. So is the technology / engine that rendered the astronomical data open source? And do members of the public have access to those tools to visualize these massive astronomical data sets, or are they proprietary?
Yes. For the most part, yes, they are available. The first slide that I showed, which was from the Sloan Deep Sky Survey, is available online. You simply have to register, and all of that data is available to anyone. Within that grouping, within that database, there is a machine learning program which will allow you to basically highlight all of the different objects in a visual field, even if you can barely not see them. The computer is smart enough to pick up single pixel objects that are very dim in the background and things like that. And that program also has all of the interactive spectra, which you can actually interact with and really show in very different ways. Some of the other data is available in bits, in no pun intended there, but in chunks. Obviously, interacting with the 4.5 petabytes of data that produced the first black hole image, that was an amazing, not only the fact that the data exists, but the real talent and the real human hand, as we've heard, in that was actually coming up with the algorithms and trying to figure out actually how to analyze this data in order to produce this image, which took a very long time. It was an extremely innovative and important project that showed, this single image. When you think the sheer volume of data and the sheer volume of computer processing that went into basically producing that single image. So as far as there are many online resources. NASA has made almost all of their data available. Sometimes it's not in the easiest form to work with. But for a first start, for people who are interested in playing around with this and looking at the way real data is displayed and being used, the Sloan Deep Sky Survey is really the best place to start.
Okay, so from the same question, you already spoke about where people could access those. Does the library license it? And then I also have a question for Whitney. If those machine-generated maps are protected by intellectual property?
It depends. So it's important to remember that the data is going to be public domain, right? That's going to be owed to everybody. For maps that are not created by humans, so if the image expression is not created by a human, that's not protected. But then there's sort of the other elements, right? So there's often a computer program that's being run, and that computer program may have some expressive code that's protected by copyright. So when we get into things like computer generation, what we're looking at is maybe not just the end result and the beginning, and then there's the stuff that that actually facilitates that process. And sometimes maybe we're not looking at something that's protected by copyright at the beginning in terms of the data, or at the end in terms of a completely computer-generated image, but then we may be looking at some copyright protection for the computer program that affects the process.
Yeah, I actually find this fascinating. I simply think it's a really interesting thing that we have the endpoint not protected, but for instance, when you think about some of these things where we are writing really innovative we're making algorithmic innovations, writing very innovative computer programs to produce the images, that the images wind up not being protected, yet the computer program does. It's quite an interesting dichotomy, because it is the human hand that's actually producing the image. It really isn't the computer, because the computer is just cranking out the zeros and ones, and out comes the image. So it's just a fascinating philosophical AI moment.
Yeah, absolutely.
Do you have any other final questions? We have about 3 minutes left.
If not, I'm happy to ask another. I'm curious, just to leave our attendees with something, where can people go today, whether they're artists or cartographers or historians, to find the Library of Congress's collection, either in person or virtually?
Well, at the moment, obviously, virtually is all they can do. Hopefully, we will get to a point where they can do it not virtually. But the Geography and Map Division, for example, has a lot of its maps online. You can just search digital collections or go to the Geography and Maps Division website, and you'll find there are now hundreds of thousands, including many of the Sanborn maps that were mentioned at one point, lots of maps that span the period from the beginnings of cartography with Ptolemy all the way to modern maps that are being created now. One caveat, of course, is all of the maps that are online and have been digitized, and this will be very helpful for our, or at least for our copyright lawyer there, that they are out of copyright or have been produced by a federal agency. So that's all you can find online. Anything that is obviously this side of 1924 that has been produced by a human creative hand, and of course cartography is very creative, won't be found there.
Great. Thank you, John, and thank you to all of our panelists for today's fascinating discussion. I also want to thank my co-moderator, Kelly, for her great job on the technical side of things. We're thankful for the Librarian-in-Residence program that we're a part of here at the Library of Congress. And we also want to thank all of our attendees. It's been a pleasure having you with us, and thank you for tuning in.